All right. So what we're going to do today, we're going to do more practice problem with acid and bases and buffers. Why? Because this is a tougher chapter. So I want to do a little more practice problems with you guys. And hopefully after today, you are going to be an expert. Now, before we do the practice problems, I want to go over and help you to identify what type of problem you have. So when you see an acid-base problem, the hardest part is identifying what type of problem you have. Once you identify, then the rest is going to be easy. So we're going to spend some time and go over when you see a problem, how to identify what type of problem you have. Ready? Let's do this. Now, when you see a problem, the first thing that you need to figure out is if you have a strong acid or base, if you have a weak acid or base. So when you see a problem, the first thing you need to do to figure out if you have a strong acid or base, or if you have a weak acid or base. Now, that part is not bad. Now, you know the strong acids. The strong acids are HCl, HI, HNO3, HClO4, and H2SO4. Am I missing one? I am. And HBr. So if you have one of these acids, you have a strong acid. If you don't have one of those acids, then you have a weak acid. So these are the strong acid. Everything else is considered weak. All right, so far so good. Now, how about strong bases? How do you know if you have a strong base or a weak base? Now, to have a strong base, remember, acid starts with H, right? The kind of Chem 1 definition. And base ends with OH. Now, to have a strong base is usually when next to the OH, we have a metal from group 1A or the bottom of 2A. Then I have a strong base. So, if next to the OH, I have a metal from group 1A or bottom of 2A, then I'm going to have a strong base. Now, let me give you an example of this. So, for example, sodium hydroxide is a strong base. Sodium is from group 1A. So that's a strong base. Let me give you another example. Barium hydroxide. That's a strong base because barium is at the bottom of group 2A. So if you have OH next to metals from group 1A or bottom of 2A, which is SRBARA, then you end up having a strong base. Everything else would consider a weak base. Now, one weak base that I want to mention because it's so common is ammonia. Don't forget that ammonia, NH3, that's the weak base. Such a common weak base that I want to mention it. All right, so strong bases, again, when you have a metal from 1A group or bottom of 2A group with an OH, you have a strong base. Otherwise, you are going to have a weak base. Now that you know this, let's go over how to identify what type of problem we have. Look at the problem. If you have a strong acid or a strong base, which you just found out how to do that, then what that means is they are going to have 100% dissociation, right? 100% dissociation. And then we do the problem from there. It's not bad. You look at the problem. What if you have a weak acid or base? Okay. What if you have a weak acid or base? Then what's going to happen? If you have a weak acid or base, that means they will not have 100% dissociation. That means I'm going to have an equilibrium. I'm going to have an equilibrium. Then you are going to do an hydrolysis. And you're going to do an ice table. And you need a Ka or Kb for weak acid or base. So look at the problem. If you have acid or base, you're going to do a hydrolysis. Equilibrium, ice table, Ka and Kb is what you need. Now, what if you look at the problem and you don't have a strong acid or base or weak acid or base? What if you have salt? Sometimes we could have a salt. What's a salt? Now, salt is when we have an ionic compound. Ionic compound is a metal or a non-metal, right? Then you have a metal and a non-metal. I'm going to give you an example of that. Example of this in this case would be, for example, KNO2 is an example. KNO2, potassium nitride. You have a metal, you have a non-metal, is an ionic compound. This is a salt. Now, when you have a salt, how would you figure it out? So if you have a salt, we've done this before, but I'm going to quickly do it to kind of remind you. When you have a salt, you need to figure out what type of salt do you have. Is a solution acidic or basic? How would we do this? Let's do a quick one to remind you. So the first one, it usually comes from the base. So the K comes from KOH. The second part usually comes from the acid. The NO2 came from HNO2. Now, so the potassium came from potassium hydroxide. That's a strong base because K is in group 1A. So if I have a strong base, what that means is the conjugate is going to be neutral. So the potassium is neutral. Now this one, HNO2, is a weak acid. If you are a weak acid, your conjugate is going to be basic. Your conjugate is going to be basic. And we've done this before. So strong base or acid are going to have a neutral conjugate. If you have a weak acid, then your conjugate is going to be basic. If you have a weak base, your conjugate is going to be acidic. So in this case, I have a neutral and I have a base. What am I end up with? I'm going to end up with a basic solution. Right? So what I'm going to end up with is NO2 minus, which is going to be a weak base, right? I end up with a weak base. Now, if I end up with a base, NO2 minus, it's a weak base. So I have a basic solution. Then what do I have to do? Remember, when we have a weak acid or base, what do? We do an ice table. You're going to do an equilibrium. And you need Ka or Kb. So far, so good? Okay. All right. So when you have a salt, figure out what is your solution, basic or acidic, and then you go from there. Now, one thing I want to make a little comment on it, and you're going to see that when I give you the salt, in most cases, what do you have to do? You would have to use Kw to get the Ka or the Kb that you need. Okay? Usually when I will do a problem like that, when you have a salt, you have to use a Kw to convert and get the Ka and a Kb that you needed. Just make a note of that and you'll see when we do practice problem. I just want everything on one page right now. So far, so good? Okay. Now, the next case, let's say you look at a problem and in that problem, you have more than one acid or base in there. Okay, let's say you have a problem and you have more than one acid or base in there. Let's say in this case you have a weak acid and its conjugate, or you look at the problem, you have a weak base and its conjugate. So you're going to end up having two things or more in the solution, right? You have a weak acid and its conjugate, or you have a weak base and its conjugate. And that's possible. Now, if you have that problem, then what does that mean? That means we have a buffer problem. So we have more than one thing in a solution. We have more than just weak acid or weak base in a solution. We have weak acid and base and it's conjugate in the solution. In that case, you have a buffer problem. And when you have a buffer problem, what are you going to do? Use the HH equation, Henderson-Hasselbalch equation. Use the HH equation. That's the easiest way to do this. Now, the last type is you look at the problem, and in that problem, you have, what does this keep happening? You have an acid and you have a base in the problem. So before you had a weak acid and its conjugate or weak base and its conjugate, now you have acid and you have a base in your problem. Then what are you going to do? So when you see a problem that you have an acid and you have a base in there, I need you to remember that acid-base are the fastest reaction in chemistry, one of the fastest reaction in chemistry. Acid-base, they like each other, they will find each other, and they will react. So if you have an acid-base reaction, if you have an acid in there, you have a base in there, you will have an acid-base reaction. And remember, the acid-base reaction, the acid will lose a hydrogen, the base will get the hydrogen. Don't forget the basic. You know the basic? You got this down. The acid will lose a hydrogen, the base will get a hydrogen. If you have an acid-base reaction, you don't have an equilibrium. It's one single arrow. If you have an acid-base reaction, you have to use moles. You have to use limiting reagent. You don't use an ICE table. Use an ICF, initial change final. Okay. Now, I want to make one more comment about this before we move on. And again, this all will make sense once we actually do practice problem. And when you have an acid-base problem, sometimes what you have to look at, you have to look at what you end up with. And you will see that. I just want everything on this page right now. So far, so good. So, very quickly, you're going to look at your problem. Say, oh, I have a strong acid or strong base, 100% dissociation. Oh, in this problem, I have a weak acid or weak base. I do an ice table. Oh, in this problem, I have a salt. Let me figure out what it is and then go from there. Oh, in this problem, I have two things. I have a weak acid and its conjugate, or weak base and its conjugate. So I have more than one thing. I have a buffer, HH. Oh, I have acid and base. So I'm going to do an acid-base problem. So the last two are the type of problem that we have more than one thing in the solution. So these two are the ones that we have more than one thing in the solution. All right, now ready to do practice problems? Let's do it. Here is our first practice problem. Which of the following has the greatest concentration of hydroxide ion? And this is the problem. Now, to do this one, we don't actually need to do the calculation. Let's see if we can figure this out conceptually. So which one has the greatest concentration of hydroxide ion? Okay. That means which one is most basic, right? Which one is most basic? Let's do this. All right. The first one, I have a pH of 3, okay? pH of 3. Now, pH of 3 is what? That's an acidic pH, right? So this is an acidic solution. Do you guys agree? This solution is pretty acidic. The second one, I have HNO2. HNO2 is not one of the strong acid. HNO3 is not HNO2. If it's not one of the strong acid, that means it's a weak acid. So it's a weak acid, but again, it's an acid. So what I end up having, I'm going to have an acidic solution, right? The next one, they give me POH. I don't like POH. I like to compare apple to apple, oranges to oranges. So what I'm going to do, I'm going to convert the POH to pH. pH, I understand. POH, I don't know. I'm not a big fan. So if I subtract 12 from 14, I get 2. So that means I have a pH of 2. That's easier for me to kind of compare. So pH of 2, that is pretty acidic, right? So this is an acidic solution. So far, so good. Okay. The next one, I have NaOH. What is NaOH? Again, Na is from group 1A with the OH. So this is actually a strong base. This is a strong base. So this solution is actually basic, is not acidic. Okay. The last one, I have ammonia. We talked about ammonia because ammonia is just so common. So ammonia is a weak base, right? So I have a basic solution, but less basic than this one because this is a weak base. You only partially dissociate. The question asks you which one has the greatest concentration of hydroxide ion. Which one is the most basic? Which one that is? Remember, NaOH is a strong base. When you have a strong base, what that means is going to have 100% dissociation into Na plus and OH minus. So every single one is going to break up into Na plus and OH minus. So I have lots of OH minus. I have lots of OH minus versus this one. This is an equilibrium. I don't have a lot of OH minus. I have some. But the strong base will fully dissociate. I'm going to have a lot of OH minus. So what's the answer? The answer would be D. All right, so far so good. Okay, let's do the next problem. Here is our next problem. When you read this problem, I give you one thing. What do I give you? I give you one thing. What I give you a weak acid. Okay? I give you a weak acid. That's what this problem is. It's a weak acid problem. Okay. That's great. I have a weak acid. Let's go over here. What do we do when we have a weak acid or base? We do equilibrium. We're going to do a hydrolysis, ice, and the Ka and Kb. So I have a weak acid. So I know what to do with this weak acid. And it doesn't matter what the weak acid is. I see a weak acid. I'm going to do an hydrolysis and I'm going to do an equilibrium. Acid is going to lose a hydrogen because acids always lose a hydrogen. So since the acid is going to lose a hydrogen, the water is going to act like a base and is going to get the hydrogen. So I'm going to end up with hydronium in the solution. Every time I have a weak acid or base, I do an ice table, right? I do an ice table. Now, the initial concentration is 0.020, okay? Minus x, x and x. I'm going a little faster because you know how to do this. I know you know how to do this. All right, so then what am I going to have? I'm going to, don't do that. I'm going to have x squared over 0.020 minus x equals Ka. Why do I need a Ka here? You need a Ka because I have a hydronium in the solution, right? It's a weak acid. All right. A little tiny problem. The problem is they don't give me the Ka in this problem. They want me to figure out the Ka. They ask me what is the Ka. I cannot have two variables. What am I going to do? Luckily, they give me another piece of information. They also give me the pH. I have a pH that is 4.93. Okay, I have to use that. Well, I know that pH is minus log of hydronium concentration, right? Again, let's take a step back. I know I have a weak acid. I do an ice table, right? I did that. I set up the equilibrium. I don't have a Ka. I cannot have two variables, and they asked me to actually figure out the Ka. So somehow I have to have the x's. And I do because they gave me the pH. Let's use a pH. pH is minus log of hydronium concentration, right? So I have the pH. The pH is 4.93 equal minus log. This is going to be my x. So I need to take the anti-log, right? That would be 10 to the x, right? I would take the anti-log, but it's minus log. So this would be 10 to the minus 4.93. So I'm taking an anti-log. If I do that, what I end up getting is 1.174 times 10 to the minus 5. That is my hydronium concentration, right? That is my hydronium concentration. Now, what is the hydronium concentration in this case? What is the hydronium concentration in this case? The hydronium concentration is the X, right? The hydronium concentration is the X. So I could just plug in that number for the X, right? So the hydronium concentration happens to be the X. So I can plug in this number. I can plug in this number over here and be able to get the Ka. So then 1.174 times 10 to the minus 5. I'm going to square that over 0.020 minus, don't forget the parentheses, 1.174 times 10 to the minus 5. Okay, so I'm going to plug everything in. Once I plug everything in, I'm going to get the Ka out of it. And the Ka would be 6.9 times 10 to the minus 9. So that is going to be my Ka. Sounds good? Okay, so we had the pH. With the pH, we've had the hydronium concentration, which happens to be the X. I plug it in, and I can get the Ka. But again, the point I'm trying to kind of get you to see today is figuring out what type of problem you have is the hardest step. And you got this. Weak acid, you do a hydrolysis, you do an equilibrium, you do an ice table. All right, let's go to the next one. All right, here's the next problem. The Kb for ammonia is given, and they ask you what is the pH. So how do we do this? The same as before. What I'm going to say is, okay, ammonia. What is ammonia? Is a weak base. So in this problem, I have nothing but a weak base. Let's go back here one more time. So I have nothing but a weak base. What am I going to do? Equilibrium, hydrolysis, ice, and Ka and Kb, right? So ammonia is a weak base. So what I'm going to do, I'm going to set up the hydrolysis. The last problem, I had a weak acid. Now in this problem, I have a weak base. Okay, I have a weak base. I'm going to set up the hydrolysis. I'm going to set up the equilibrium. Remember, base will get a hydrogen. So the ammonia is going to get the hydrogen, which means the water is going to act like an acid and is going to lose a hydrogen. The base gets a hydrogen. The acid loses a hydrogen. I'm going to do an ice table because I have a weak base. Okay, nothing has changed. You guys got this down. The initial concentration is 0.35. So minus X, X, and X. Again, I'm going a little faster because you guys know this part. I know you do. So then I'm going to set up the equilibrium. Okay, equal what? Set up the Ka, Kb. Again, why are we having Kb here? We are having Kb here because we are dealing with a basic, right? I have an OH minus solution. Now, do I have the Kb? Yeah, the Kb is given in this problem. It's 1.9 times 10 to the minus 5. Okay, so what's not bad? What I have to do, I have to solve for X, right? And I am going to assume that this is 0 to make my math a lot easier. Now, if I do that, what I end up for X is 0.002578. Okay, so I have the X. Okay, now what is the X? The X is hydroxide concentration. Okay, the X is hydroxide concentration. So what could I figure out when I have hydroxide concentration? I can figure out the pOH, right? I have a hydroxide concentration. I can figure out the pOH because pOH is going to be minus log of OH concentration. Okay, so I can figure out the pOH. In this case, it would be minus log of that number. When I put in a calculator, what I end up getting for pOH, I end up getting 2.959. I get 2.59. Okay. And again, I subtracted from 14 to get the pH. So the pH would be 11.41. That is going to be my pH. I have an OH. I figured out pOH as the easiest way. Subtract from 14 and you figure out the pH. Yeah, this was a weak base problem. So far, so good. Okay, let's go to the next one. So here's our next problem. I give you the Kb of methylamine and I ask you for the pH of this solution. Now, there's only one thing in a solution, so you need to figure out is it a strong acid or a strong base, or weak acid or weak base. You know it's not a strong acid or a strong base, is not one of the ones that you know. So it's going to be weak acid or base, right? Because it's not on the list of the strong acid and it's not on the list of the strong bases. So it's going to be a weak acid or base. Now I give you the Kb. By giving you the Kb, I'm kind of giving it away that this is a weak base. Because remember, first of all, only weak acid and weak bases have Ka and Kb. So if you have a weak acid, you have a Ka, and when you have a weak base, you have a Kb. So sometimes we can look at the problem and look at these little details and be able to figure out what type of problem you have, or to confirm what type of problem you have. So methylamine, I know, is a weak base. Is not on my list. Also, I give you the Kb, right? So it's going to be a weak base. Now I want to kind of go over this one because it's a little bit cool to go over this. So methylamine. Methyl is CH3. So this is CH3NH2. I want to draw this out. So CH3NH2. This is a methylamine. And what makes this to be basic? And amines are basic because it's the lone pair on nitrogen. So amines are usually basic because the amine, the nitrogen has a lone pair. Now, what does that lone pair mean? When you have a lone pair, that means you can afford to get the hydrogen. Because acid needs to have a hydrogen to give away, needs to have an acidic hydrogen to give away, and a base needs to have minus charge or an electron pair to get that hydrogen. You need to be able to afford that hydrogen. And this one does, so amines, nitrogen has a lone pair, so it can get the hydrogen. And these H's, these hydrogens are not acidic, so they're not acidic. But amines are usually basic because the nitrogen has a lone pair to be able to get the H. Alright, so I have a Kb. I know this is a weak base. Now, if I have a weak base problem, now you know how to approach this, right? I have a weak base problem. How would you approach this? Hydrolysis, right? Hydrolysis, equilibrium, and the base is going to get the hydrogen. That means the water is going to lose a hydrogen, act like an acid. Okay, so far so good. So it's a weak base problem. Again, the same as before. Nothing has changed. Doesn't matter how fancy of a weak acid or weak base I give you, everything is going to be the same. And even if you don't know the formula for a weak acid or base, doesn't matter. Just make up a formula. Doesn't change the numbers. So the initial is 0.3500 minus x. Again, it doesn't matter how fancy of the base or acid I give you. You can just make up a formula for yourself or just use x and solve the problem. So I have the Kb, which is 4.4 times 10 to the minus 4. So if I do that, again, as before, I'm going to assume this is 0. I can do that because this is such a huge number compared to that, right? The Kb is so small compared to that. I can definitely assume is 0. So what I get for x is 0.01241. Okay, so I have the x. Then what am I going to do? What is the x? What the x is here is going to be my hydroxide concentration, right? The x is going to be the hydroxide concentration. Again, remember, I know you know this, but this is a Kb because I have a base. I have an OH minus in the solution. So I'm going to use a Kb. All right, so when I get the X out, the X is going to be the hydroxide concentration. The same as before, when I have the hydroxide concentration, it's much easier to figure out the pOH, right? Much easier to figure out the pOH because minus log of OH concentration is going to give me pOH. So the pOH would be 1.90 minus log of the OH concentration gives me pOH. But again, I'm going to subtract it from 14. Don't do that. And I get 12.09. That is going to be my pH. Okay. Here is the next problem. What is the pH of a 0.030 molar solution of KF? What is KF? Weak acid, weak base, strong acid, strong base? No, this is a salt, right? So this is a salt. So now we have a solution is a salt. Again, I'm going to keep going back to this, right? Figure out where you are on this chart. It's not a strong acid or weak acid. It's a salt, right? If we have a salt, what do we need to do? We need to figure out what type of salt this is. So I have a KF. Right? Let's figure out what type of salt is KF. So here's KF. And we said that the first part usually comes from the base. So the K comes from KOH. And the second part usually comes from the acid. So it comes from the HF, right? Because acid has a non-metal and base has a metal. Okay, and then acid is a metal and a non-metal. So the first part, the metal from the base. The second part, the non-metal from the acid. Okay. So now KOH, you know, is a strong base, right? 1A group. So if you're strong base, your conjugate is going to be neutral. Now, HF is a weak acid. If you are a weak acid, your conjugate is going to be basic. Your conjugate is going to be basic. So what I have F minus, which is going to be basic, is going to be a weak base. So far, so good. Okay, so what I end up having, I have a weak base. F minus is a weak base. Okay, it's not one of the strong bases, right? It's going to be a weak base. And again, it's a base because it has a minus charge. Remember, bases have a minus charge, have a lone pair to be able to get a hydrogen. All right, so what am I going to do? What I'm going to do, I'm going to set up an ice table because I have a weak base situation. I'm going to set up hydrolysis. I'm going to set up an ice table. The base is going to get a hydrogen, okay? And that means the water is going to react like a acid and is going to lose the hydrogen. And now I'm going to do an ice table. Again, in this problem, I had a salt. I figured out what type of salt I have. This is a basic solution, right? So I'm going to do a weak base hydrolysis in here. And the initial is 0.030, okay? Minus x and x. Again, I'm going really fast because you guys know this really well. X squared 0.030 minus x. What do I need here? I need a Kb here, right? I need a Kb here because it's a OH minus concentration. But what is given to me? Ka. So what do I need to do? I need to figure out the Kb using Kw. And you know, I love my chart at the beginning. Remember I said, put this on there. We usually use Kw to get what we needed, the Kb and the Ka that we need. When you have a salt, you usually have to worry about that. And that's in there. So have this in front of you as you do in practice problem. Okay, so again, I needed a Kb because this is a base, right? This is a OH in the solution, is a base, so I need a Kb. But what can I do from that? Yeah, I can figure out the Kb using the Kw. Using the Kw, I can figure this out. So far, so good. Okay. So I need a KB. So what I'm going to use KW over KA is going to give me the KB, right? KW over the KA is going to give me the KB that I needed. So if I actually do the math, and remember the KW is 1 times 10 to the minus 14. If I do all the math, and I'll tell you what I got for KB, and I keep doing that. 1.388 times 10 to the minus 11 is what I got. So I'm going fast because you guys know how to do the math. I'm sure you do. I'm going to solve for KA. Okay. Solve for X. This is my X. This is my X. Now, what does X represent? X is my hydroxide concentration. X is my hydroxide concentration, okay? X is my hydroxide concentration, okay? If I have a hydroxide concentration, what can I figure out? I can figure out POH because minus log of OH minus gives me POH. I'm not going to do this because you guys know it. So I get 6.19 for POH. Subtract it from the 14 and I get 7.81, and that is going to be my pH. Okay, that is going to be my pH. So far, so good? Okay, so again, really quickly, the point was I have a salt. Figure out what type of salt you have. Is it basic salt? I'm going to do a weak base hydrolysis. You set up the ice table. You set everything up. Remember, it's a base solution. It's a basic solution. You need a KB. So we need to have to solve for KB using KW. I figure out X. What X is OH minus concentration. POH is minus log of OH minus. I got a POH. Subtract from the 14 and I get the pH. All right, beautiful. Let's do the next one. Here is the next problem. I ask you for the pH of a solution that is 0.12 molar HOCl and 0.20 NaOCl. Now I have two things in the solution. So far, everything we did had one thing in the solution, right? Now I have two things in the solution. Okay. I have buffer or I have acid bases. Which one do I have? This is a weak acid. Is not one of the strong acids. Starts with H. So this is a weak acid. And this is its conjugate. Right? The OCl is a conjugate of that. So it's an acid. Starts with H. Is a weak acid because it's not one of the acids on the list. And then the OCl is a conjugate of it. So what I have here, I have a buffer problem. The buffer problem, I'm going to do the Henderson-Hasselbalch equation. Is the easiest one, okay? So pH equals pKa plus log, and the acid goes concentration of acid, and the conjugate goes on top, okay? Let's do this. So the pH equals pKa, okay? How do you figure out the pKa? Minus log of Ka gives me the pKa. Minus log of Ka give me the pKa. If you do that, you get 7.45. Again, this is a review. I'm going to skip those steps. So the minus log of Ka gives me pKa. Okay. Now the acid is 0.12 and the conjugate is 0.20. If I do everything, I love this equation. 7.68. I get 7.68. And I think for the KB, when I do the correct one, I got 7.46. Double check the math for me. All right, so here is, if you're a little off, that's okay. So here is my pH. I really like the Henderson-Hasselbalch equation. Again, pH equals pKa plus log, concentration of the acid and the base. And I have a Ka minus log of Ka gives me pKa. So this was a buffer problem. Ready for next one? Let's do the next one. Here's our next problem. Okay. I also have two things in here. I have a HCl and I have ammonia. I have two things in here. It's not a buffer problem, right? HCl is a strong acid and I have ammonia, which is a weak base. So I have two things here. I have a strong acid and I have a weak base. I have an acid and I have a base. It doesn't matter if it's weak or strong. I have an acid and I have a base. Every time you have an acid and you have a base, what are you going to have? You are going to have an acid-base problem. Let's go back to this chart. So, when I have more than one thing in a solution, it could be a buffer if I have a weak acid and its conjugate, or weak base and its conjugate. We just had that. Or if I have acid and base in the solution, I have an acid-base reaction. And when you have an acid and base, it doesn't matter if you have a stronger base. If you have an acid and you have a base, the acid and base are going to react. I'm going to have an acid-base reaction. So in this case, I have an acid and I have a base. I'm going to have an acid-base reaction. So ammonia plus HCl, one arrow. The base is going to get a hydrogen. The acid is going to lose a hydrogen. That never changes. The base is going to get a hydrogen. It's going to become ammonium. And the acid is going to lose a hydrogen. It's going to become Cl minus, ammonium chloride. So far, so good. Okay. What am I going to do? I'm going to do an ICF. So again, I have an acid, I have a base. Doesn't matter if it's a weak or strong. As long as you have an acid and you have a base in a solution, you are going to have an acid-base reaction. Okay, so I have to do moles. Okay, I give you moles, which is kind of nice. I have 0.10 moles of HCl. And this is molarity, but it's 1 liter. So it would be 0.25 moles of ammonia. Okay. I also have to do a limiting reagent. So acid base, 1 arrow, moles, limiting reagent, ICF. What's my limiting reagent? Which one am I going to run out first? Limiting reagent is my HCl, right? This is my limiting reagent. So minus 0.10 minus 0.10 plus 0.10. I'm going to have none of the limiting reagent left as expected. Oh, I'm going to do math in my head. 0.15, right? And 0.10. Okay. What I end up having left, I have ammonia left and I have ammonium left. Oh, I love this chart that I put up here. I said, look at what you end up with when you have an acid-base reaction. Look at what you end up with when you have an acid-base reaction. What did you end up with? You ended up with ammonia and ammonium. Weak base and its conjugate. You end up with a weak base. Ammonia is a weak base. And this is its conjugate. So I end up with buffer problem. That's pretty cool, right? We end up with a buffer problem. That's perfect. I have a buffer problem. I'm going to use the HH equation. Now, this is a weak base problem. So, POH equals PKB plus log ammonia here and ammonium on top. All right, let's plug it in. PKB again. I have the KB minus log of KB give me PKB. In this case is 4.74 plus log ammonia is my 0.15. Ammonium is 0.10 and is 1 liter solution. So the moles and molarity will be the same. Again, because I'm dealing with a base, okay, I'm going to use the POH. And if I do this, what I get for POH, I get 4.56 is my pOH. I subtracted from 14 to get the pH. If I do that, I get 9.44. That is my pH. Okay. Again, in this problem, when you looked at the problem, you go, oh, I have two things, okay? So it's not just a strong acid or a strong base or weak acid or weak base or salt. It's none of that because I have two things. It's not a buffer right off because I don't have a weak base and its conjugate. HCl is not a conjugate of that. So I have an acid, I have a base, I have an acid-base reaction. Acid-base reaction, one arrow, limiting reagent, moles, ICF. I do that, then I look at what I end up with. I ended up with a buffer, so I use that the HH equation. Because it's a weak acid and its conjugate, weak base and its conjugate, I use a pOH because I'm dealing with base. Once I figure out the pOH, I subtract it and I got the pH. All right, ready for the next question? Let's do this. All right, here is our last problem. Now, which of the following could be added to a solution of sodium acetate to prepare a buffer? Sodium acetate, I'm going to put abbreviated as sodium is Na, acetate as AC. I've done that before. So sodium acetate, really quickly, this is a salt, right? I'm looking for a buffer solution. Na comes from NaOH, right? So Na is neutral because NaOH is strong base. The second part, acetate comes from acetic acid, right? Acetic acid is a weak acid, so this is going to be basic. Okay. We just wanted to kind of go over this, see what are we dealing with before we look at the options. So we want to make a buffer. We want to make a buffer solution. The first option is, what if we add 0.10 molar acetic acid? So what happens if I add acetic acid? That's perfect. If I add acetic acid to sodium acetate, what do I end up having? I end up having a buffer pair, don't I? Right? Because if I add 0.10 acetic acid to 0.10 sodium acetate, that's a 1-to-1 buffer ratio. That's a great buffer. So yeah, that could work. That could definitely work. Okay, how about the next one? What if I add HCl to sodium acetate? What happens? Now, don't rush on this one. HCl is an acid. Sodium acetate, we just said that's more on a basic part. Neutral basic is going to be base. So I'm going to have an acid-base reaction. I'm going to have an acid-base reaction here. Okay, so let's do this acid-base reaction. So I have HCl plus this AC minus, right? We talked about it over here. That's because Na plus is just neutral, not going to do anything. So I have my acid and I have my base. So acid is going to lose a hydrogen, base is going to get a hydrogen. So this is going to be HAC. And then of course, you know how we had that Na and then the Cl would make it NaCl, right? Because sodium acetate, the sodium and the Cl, they're going to have a NaCl. Again, it's neutral, it's not going to do anything. But the point is here, I had an acid, I had a base, acid-base reaction. Acid is going to lose a hydrogen, base is going to get a hydrogen. I'm going to end up with HAC, okay? Now, could this work? The HCl, I have 0.05 and I have 0.10 molar. Okay. What is going to be my limiting reagent? HCl is going to be my limiting reagent. So I'm going to have 0.05 minus 0.05 plus 0.05. None of that is going to be left over. what am I going to have somewhere left over? I'm going to have 0.05 of this and 0.05 of that left over. So what am I going to end up having with this problem? I'm going to have acetate and acetic acid. What do I end up having? I end up having a buffer problem, right? So yes, this could definitely also work. So far, so good? Okay. Again, don't write it off when you have an acid and base. Do an acid base. See what you end up with. I have an acid here. I know sodium acetate is basic, so I have an acid-base problem. Acid loses a hydrogen, base gets the hydrogen. By the way, if this is confusing to you guys, you see I can put the sodium back in here so you can see where the sodium NaCl comes from. So this is going to lose a hydrogen. This is going to gain a hydrogen. I'm going to have HAC. NaCl, again, is a neutral salt, not going to do anything. Acid-base problem, one arrow. I have to do ICF. I have to do limiting reagent. Acid is my limiting reagent. So what I end up having is I'm going to end up having some of the acetate and acetic acid. I end up having a buffer pair. So yes, that could actually work too. It would have not worked if HCl was not a limiting reagent. Okay, let's go to next one. Next one, I have ammonium acetate. Ammonium acetate. Would that do anything? No, because I already have some acetate. I have ammonium acetate and more acetate. That's not going to do anything. Now, how about NaCl? Would NaCl do anything? No, that's a neutral base. NaCl is a neutral base. It's a neutral base, is not going to do much. Okay? So, yes, the two that are going to work, if I add this and I add this, I would end up having a buffer problem. So yeah, those two actually work. Where it says NaCl, neutral salt, not going to do anything. Acetate, I already have acetate. I don't need that. I need acetic acid or make acetic acid to do that. Sounds good? Okay. All right, nice job. So hopefully now you can identify what type of problem you have. I'm going to go back to this chart. Everything goes back to this chart. If you have one thing, see if it's a strong acid or strong base, or weak acid or weak base. If you have one weak acid or one weak base, you're going to do ice table. What if you have salt? Figure out what type of salt it is. Is it like a weak base or weak acid salt? And then go from there. Now, what if you have more than one thing in a solution? Then you might have a buffer if you have a weak acid and its conjugate, or weak base and its conjugate. Or if the two things you have in there, you have an acid and base, do an acid-base problem and then see what you end up with. All right. Nice job. Nice job. Hopefully you guys are doing more practice problem and understanding this.